Hi everyone, hope everybody's doing well. And this is our chapter 20. We're going to be learning about thermodynamics in this section. We also talked about thermodynamics in General Chemistry 1 also, correct? So here we're going to learn mainly about entropy, free energy and the direction of chemical reactions. So we are learning the second law of thermodynamics. We predict the spontaneous change of a reaction. We're going to calculate the change in entropy of a reaction and then see what is the relationship between entropy, free energy and the work, and free energy equilibrium and reaction direction. So what is a spontaneous change? So spontaneous change is one that occurs without a continuous input of energy from outside the system. Once a spontaneous process has started, we do not need to give energy for it to continue. It just happens by itself. Okay? So all chemical processes require energy, which is called activation energy, to take place. But once a spontaneous process has begun, no further input of energy is needed. A non-spontaneous change occurs only if the surroundings continuously supply energy to the system. If a reaction is not spontaneous, then the surrounding has to give energy continuously for that reaction to keep going. Okay? If a change is spontaneous in one direction, it will not be spontaneous in the reverse direction. Okay? It would be only spontaneous in one direction. The first law of thermodynamics does not predict spontaneous change. Anyone remember the first law of thermodynamics? Remember, we talk about the energy is conserved. It is neither created nor destroyed, but is transferred in the form of heat and or work. Hope you guys remember this equation that we said that the delta E, change of energy, equals Q plus W. Q here is the heat and W is the work. The total energy of the universe is constant. So this is energy. Delta E system equals delta E surrounding, but the opposite sign. Or we can say delta E system and the delta E surrounding equals the delta E of the universe, which includes 0. Okay. The law of conservation of energy applies to all changes and does not allow us to predict the direction of a spontaneous change. And delta H, we also learn about delta H. So delta H also does not predict a spontaneous change. Delta H will tell us whether a reaction is exothermic or endothermic. Okay, so but the spontaneous change could be either exothermic or endothermic. Spontaneous exothermic processes include, so these are some of the familiar examples, exothermic processes. Freezing and condensation at low temperatures. We have all experienced freezing and condensation. When the temperature is low, it just happens. So that is a spontaneous exothermic process. It releases heat when it happens. Combustion reactions, okay, and oxidation of iron and other metals. If you have a piece of iron, you would see that it corrodes, and that is the oxidation. That is also a spontaneous exothermic process. So some of the spontaneous endothermic processes include melting and vaporization at higher temperatures. When the temperature is high, you can see things can melt, even the ice, that we had snow recently. And as the temperature increases, we could see that the ice and the snow melts. That's the endothermic process. It absorbs heat from the surrounding to melt. And then another one, dissolving of most soluble salts. Let's say even your table salt, sodium chloride, you put it into water, it just dissolves. Okay, so that is a spontaneous process, and at the same time it's an endothermic process. It absorbs heat from the surrounding for the salt to soluble. Okay, so the sign of delta H. Now you see the first three examples are exothermic, delta H is negative. The last two, this is endothermic spontaneous processes, but the delta H is positive. So you can see here sometimes delta H positive for a spontaneous reaction, sometimes delta H is negative for a spontaneous reaction. So the sign of delta H does not by itself predict the direction of a spontaneous change. Freedom of particle motion. Now what is entropy? How can we increase an entropy of a system? We can do that by increasing the motion of the particles in the system. Let's look at here. All spontaneous endothermic processes result in an increase in the freedom of motion of the particles in the system. For example, solid goes to the liquid, liquid become gas. When is this going to happen? So solid need to absorb heat from the surrounding in order for it to become liquid. So solid becoming liquid is endothermic or exothermic. It is endothermic. Let's say you have ice cubes, it need to absorb heat from the surrounding, which is endothermic, to become liquid. And then if you have liquid water, it can evaporate. So again, as the temperature is increased, so then it becomes gas. So this is an endothermic process. So result in increase in the freedom of the motion. Do you see what happened to the motion of the particles? So the solid particles are very closely packed with each other. Excuse me. And the liquid particles have more freedom of motion, and then as it become gases, the gas particles are even more separated out and they have freedom of motion more. So it increases the freedom of motion of the particles in the system. Excuse me. Another example, crystalline solid plus liquid. Like your salt, sodium chloride, which is a crystalline solid, you put it into the water. Now it become ions in the solution, sodium ions and the chloride ions. So the water molecules will come and surround the ions. Again, that is an endothermic reaction. Again, what you are seeing here is crystalline solid is sodium chloride, NaCl, and then when it become ions, it becomes sodium ions and the chloride ions. So we have ions in the solution. So this is one molecule. Now it has two. So it increased the freedom of motion of the particles. So what we are seeing here, less freedom of particle motion become more freedom of particle motion. Localized energy of motion become dispersed energy of motion. So that tells us it increases the entropy. A change in the freedom of motion of particles in a system is a key factor affecting the direction of a spontaneous process. Okay, so if you can see a bigger molecule become less, like for example sodium chloride, a complex molecule becomes sodium ions and the chloride ions to become two particles, so it increases the freedom of motion. One become two. Okay, and then very compact, though, like the solid become liquid, liquid become gas. All of these are giving us more freedom of motion. So that indicates us a direction of a spontaneous process. Microstates and dispersal of energy. Just as the electronic energy levels within an atom are quantized, a system of particles also has different allowed energy states. Remember in Gen Chem 1 we learned about when we were studying energy levels of an atom, we said that you can have energy levels N1, N2, N3, N4, N5, N6 and so on. And likewise, a system of particles also has different allowed energy states. Each quantized energy state for a system of particles is called a microstate. Okay, At any instant, the total energy of the system is dispersed throughout one microstate. If you just take one instant, the total energy of the system dispersed throughout one microstate. At a given set of conditions, each microstate has the same total energy as any other. Each microstate is therefore equally likely. You can have many microstates, but they are equally likely and they also have the same total energy as any other. The larger the number of possible microstates, the larger the number of ways in which a system can disperse its energy. Okay, let me show you that in a state. Okay, I'll show you in a few slides down the road. Okay, now the entropy. So we can correlate this entropy to the microstates. The number of microstates, let's give the W symbol, the number of microstates in a system is related to the entropy of the system. Meaning the more number of microstate a system would have, entropy would increase. Okay, so there is a formula, entropy equals K ln W. K is a constant. W is the number of microstates. A system with fewer microstates has lower entropy. A system with more microstates has higher entropy. All spontaneous endothermic processes exhibit an increase in entropy. Okay, spontaneous endothermic processes exhibit increase in entropy, meaning it would have more microstates. Entropy, like enthalpy, is a state function and is therefore independent of the path taken between the final and the initial states. Now, this is an example of spontaneous expansion of a gas. Let's say you have 2 flasks and then the gas is confined to this part and then the valve is closed. When the stopcock is opened, the gas spontaneously expands to fill both flasks. Now this is closed, so you open it. When it opens, what happens? The gas will go through this tube and fill up the other part as well and then become equally distributed. Now, in order to do that, do we have to push the gas from this side by other means? No, right? It just expands. Because the space is there, the gas expands. That is a spontaneous change, expansion, right? Increasing the volume, what we are doing here is increase the number of translational energy levels. In other words, the microstates. Energy levels the particles can occupy. So now this particle that was in this space has more space. Now the particles can exist. Okay. The number of microstates and the entropy therefore increases. Meaning the more space, the particles can disperse more. Okay. Like this. This is an example of entropy increase due to the expansion of a gas. Just the same thing that we had seen here in the previous one. So this axis represents the energy. So this is when you have one flask and when you open this top cork, so the space became double. Now what happened? Here you have 1, 2, 3, 4 microstates. Here you have 1, 2, 3, 4, 5 microstates. Here the mole atoms in the gas particles are more close. Now it is more dispersed. Increased number of microstates. Opening the stopcock increase the number of possible energy levels which are closer together on average. More distributions of particles are possible. Okay. Delta S for a reversible process. Now, if you want to find out the delta S for a reversible process, we can use this equation delta S system equals Q reversible over the temperature at which the entropy we want to find out. Q here is the heat and T is the temperature. Okay, a reversible process is one that occurs in such tiny increments that the system remains at equilibrium and the direction the change can be reversed by an infinitesimal reversal of conditions. For example, let's look at this diagram simulating a reversible process. A sample of neon gas, so this is a neon gas, confined to a volume of 1 liter by the pressure of a beaker of sand on the piston. There is a piston, there is a 1 mole of neon gas, and then there is a beaker with some sand in it. If you remove just 1 grain of sand, that can be called as infinitesimal change. When you remove sand, what happened to the pressure? It decreases. As the pressure decreases, what happened to the volume? It increases. If the pressure decreases, then the volume of the neon gas will increase. In other words, it would cause the gas to expand a tiny amount. And then, who is doing the work? Gas is doing the work. The gas does work on its surroundings, absorbing a tiny increment of heat, Q, from the heat reservoir. This simulates a reversible process, since it can be reversed by replacing the grain of sand. And if you put the grain back here, so then the pressure will increase and then the volume will decrease, and then instead of absorbing heat, it would release a little bit of heat. So that is a reversible process. The second law of thermodynamics. The sign of delta S for a reaction does not by itself predict the direction of a spontaneous reaction. If we consider both the system and the surroundings, we find that all real processes occur spontaneously in the direction that increases the entropy of the universe. Meaning, if you are increasing the freedom of motion, so the universe expands its entropy, the freedom of motion. Okay, for a process to be spontaneous, a decrease in the entropy of the system must be offset by a larger increase in the entropy of the surroundings. So this is the delta S. The universe, delta S of the universe will increase greater than 0. Meaning delta S system and the delta S surrounding is also going to be greater than 0. Okay. Excuse me. Comparing energy and entropy. The first law of thermodynamics says the total energy of the system or the total energy of the universe remains constant. That is the first law of the thermodynamics. Delta E system plus the delta E surroundings equals the delta E of the universe, which is 0. Most of the time, we can use delta H to approximate delta E. Often used to approximate delta E. For enthalpy is delta H. There is no 0 point. We can only measure changes in enthalpy. The total entropy of the universe increases. Delta S universe, which is going to be the delta S system plus the delta S surrounding, is going to be greater than 0. So when we are comparing energy and the entropy, okay, delta S increases in the universe, whereas delta E is a constant. For entropy, there is a 0 point, and we can determine absolute entropy values. For enthalpy, there is no 0 point. How do we make a 0 point for entropy? Let's look at a perfect crystal, meaning there are no movement. It's a perfect crystal solid, has zero entropy at absolute zero. Okay, so remember, entropy of the system we can measure using this equation. S equals K ln W. K is a constant, W is the number of microstates. If it is a perfect crystal at 0 degrees, there is no movement at all, so then it has only one microstate. If W equals 1, ln 1 equals 0, so the entropy would be 0. A perfect crystal has flawless alignment of all its particles. At absolute zero, the particles have minimum energy, so there is only one microstate. So K ln 1 will become 0. Okay. Standard molar entropies. It is given the symbol S naught, standard molar entropy of a substance, measured for a substance in its standard states in units of joules per moles per Kelvin. The convention for defining a standard state include 1 atmosphere for gases. So we want to define the pressure is going to be 1 atm, and if it is a solution, it's going to be 1 molar for solutions, and the pure substance in its most stable form for solids and liquids. Those are the conditions for standard molar entropies. There are some factors that affect entropy. Let's look at these factors. Entropy can depend on temperature. For any substance, standard entropy increases as the temperature increases. Entropy also depends on the physical state of a substance. Entropy increases as the phase changes from solid to liquid to gas. The formation of a solution affects entropy. Okay. Remember, sodium chloride dissolved in water become soluble particles, that increases entropy. Entropy is related to atomic size and molecular complexity. As the atomic size and the mass increases, entropy increases. The more complex molecules has more entropy compared to a less complex molecule. When we are comparing, we want to make sure we compare substances in the same physical state. If we are comparing two objects, it has to be both either in the solid, liquid or gases. Now the first one we said entropy depend on temperature. Now these factors, let's look at with some diagrams what it means. Visualizing the effect of temperature on entropy. Conceptual diagram. Now this axis represent energy. Okay. A system of 21 particles. So there are 21 particles over here. Occupy energy levels. There are some lines and we call them as microstates 1, 2, 3, 4 in a box, whose height represent the total energy. So this is the total energy height. When heat is added, so we increase the temperature by adding heat. What happened? The total energy increases and becomes more dispersed. So entropy increases. When you add the heat, adding heat means, remember, energy equals Q plus W. So when you add Q, you have a certain amount of heat here, you add more heat, so then the energy increased. As the energy increased, it has more microstates and the entropy increases, more dispersed, more motion of freedom for the particles. Okay. And then we talk about the second factor, which is entropy depend on the physical state of a substance going from solid to liquid to gas. We can see here, this is a solid. Okay, it has a certain amount of entropy, let's say about 40. This axis is entropy, and it become a liquid. A liquid has a certain entropy 120 here, and then you add more heat and then it become gases. So when it become gas, it has more freedom of motion, so higher entropy, about 200. Okay. Entropy change accompanying the dissolution of a salt. You put a salt into water, how entropy increases. Now this is a pure solid. This is a pure liquid water. Let's say this is your sodium chloride. You put it into water. Now the pure solid particles are sodium ions and the chloride ions are very close to each other and less freedom of motion. You mix it with water, what happened? Now the ions are separated. Solution. The entropy of a salt solution usually greater than that of the solid and of water, but it is affected by the organization of the water molecules around each ion. So it increases the entropy. Entropy of a gas dissolved in a liquid. Let's say these are gas particles. So gas can dissolve in water. What happened when it dissolved in water? Has the movement increased or decreased? It decreased. So what happened to the entropy of the gas particles? It decreased when it's soluble in water. Entropy of a gas is already so high that it decreases when the gas dissolves. Okay. Entropy and the size of the atom. Entropy is higher for a larger atoms or molecules of the same type. So this is lithium, sodium, potassium, rubidium, cesium. These are elements in our first group. Atomic radius, molar mass and entropy given. So this is as you go down the periodic table. You can see the size increases. Size increases, molar mass increases. So what happened to the entropy? Entropy also increase. Okay, size increases, molar mass increases, entropy increases. And these are molecules. Hydrogen fluoride, hydrogen chloride, HBr, HI. These are their molar masses, and then entropy also increased as the molar mass increases. This shows us as the molecule become more complex, what happened to the entropy. Entropy, vibrational motion and molecular complexity. This is nitrogen monoxide, one nitrogen, one oxygen. You can have another molecule with more oxygens, NO2. Now it has two oxygens. Now this is N2O4. There are two nitrogens, four oxygens. Now this has only one motion, symmetrical vibration. This can bend, this can stretch. This has even more complex motion. So which one would have more entropy? The more complex the molecule become, more of its freedom of motion. As a result, it would have the highest entropy. So for compounds, entropy increases with chemical complexity. Now we have some questions. Choose the member with the higher entropy in each of the following pairs and justify your choice. 1 mole of sulfur dioxide gas or 1 mole of sulfur trioxide. Which one do you think would have a higher entropy? 1 mole, 1 mole. And SO2, SO3. SO3 is more complex. It has one more atom than this one. So it would be SO3. 1 mole of carbon dioxide solid, 1 mole of carbon dioxide gas. Solid or gas? Gas has more freedom of motion. So 1 mole of carbon dioxide will have more entropy. C. 3 moles of oxygen or 2 moles of ozone. Here, if you look at the molecule complexity, this is 2 oxygens, this is 3 oxygens. But there are 3 molecules of this and this is 2. So in this case, even though there are 6 oxygen atoms, 3 times 2, 6, 2 times 3, 6 oxygen atoms in both cases, the number of molecules 3 here would win over 2 moles of ozone. That will give you more freedom of motion, 3 moles of oxygen. So this would have a higher entropy. 1 mole of potassium bromide solid, 1 mole of potassium bromide aqueous. Which one would have more freedom of motion, solid or the potassium bromide in the aqueous medium? It would be the soluble one, right? KBr in water. Aqueous means dissolve in water. Sea water at 2 degrees Celsius or 23 degrees Celsius. We learned as the temperature increases, has more microstates, so it would be higher temperature seawater. 23 degrees would have higher entropy. 1 mole of carbon tetrafluoride or gas or 1 mole of carbon tetrachloride gas. Again CF4, CCl4, both are gases. What do we need to look at? You need to look at the molar masses. Fluorine versus chlorine. Fluorine molar mass is 19, I believe, right? Whereas chlorine is 35.45. So chlorine CCl4 has a higher molar mass compared to CF4, so this would have a higher entropy. Okay, you can also see the explanation here.